We want to generate functions for division and square root within our floating point unit. Now we're going to use an approximating method. So this method is going to be fast, but it won't be necessarily as accurate as other methods. I chose this method simply because it was a really interesting algorithm and quite a famous algorithm historically within computer science. So the algorithm is called the fast inverse square root algorithm, and it first appeared in a game called Quake 3 Arena. They wanted to render the graphics in this game a lot quicker so that the game ran a lot smoother. Now whenever they're rendering the graphics, they're really working out the normalization of millions of vectors. So this algorithm allowed them to do this really quickly, but with a little bit less accuracy. We're not going to get into all of the mathematical details of the fast inverse square root algorithm in this course. I have another course which covers the 32-bit floating point unit division and square root algorithm, and if you're interested you can have a look at that course. It goes into this algorithm in a lot more detail, and it also describes the actual logisim realization of the circuit in more detail as well. What we're going to have here are just one or two videos to give us a good flavour of this algorithm and how we implement it. Now we're going to start off here at this little mathematical function, y is equal to 1 upon root x. And the fast inverse square root algorithm is going to approximate this little function. So let's say, for example, we put the number 4 in for x. We get y is equal to 1 upon the root of 4, which is 1 upon 2, which is 0.5. So the fast inverse square root algorithm in effect is going to take in the number 4 and it's going to give us the number 0.5 out. Now a thing to note here is that what we're generating here is the square root, but then it's going to be the reciprocal of the square root, that is 1 upon the square root. But the algorithm is called fast inverse square root. But we aren't actually generating the inverse, we're generating the reciprocal. Although in computer science, this algorithm has become known historically as the fast inverse square root algorithm. Now, here is the algorithm here, and it's quite a simple and straightforward algorithm. We're going to have this number ix, which is the input, and the algorithm will give us this number iy, which is the output. And it does this by taking the ix, dividing it by 2, and it subtracts the result away from this term here, 3 upon 2 times lb. So what are the terms L and the terms B? Well, the term L is the number of mantissa values. So for example, in a 16-bit floating point number, we're going to have 10 mantissa bits. So we're going to have 2 to the power of 10 mantissa values. So that's going to be 2 to the power of 10. The B is going to be the exponent bias. So again, in a 16-bit floating point number, we've got 5 exponent values, and the bias is a value of 15. So we're going to finally have 3 upon 2 times 2 to the power of 10 times 15. So this number here is 23040. So the contention then is that we can work out the reciprocal of the square root of the value ix by dividing ix by 2 and taking it away from this number. Now this number here has become known as the magic number. And you could well understand why people would look at this as a little piece of mathematical magic. If you haven't gone and derived exactly where this number comes from mathematically, then it kind of looks like it's been pulled out the air. But again, if you're interested in all of the details, then you can go and do the full course on the division and square root algorithms. So what are these numbers ix and the iy? Well, they're not the numbers 4 and 0.5, but they are those related to those numbers. So what we do is that we take the value that we're trying to find the reciprocal square root of, and we write it in our 16-bit floating point representation. So this here is the 16-bit floating point representation of the number 4. And you can work out that because you've seen in the previous videos, we're going to have the exponent bit here, well, that's going to be 16 plus 1, which is 17. We take away the bias, which is 15. So 17 minus 15 is 2. So that's 2 to the power of 2, which is 4. The mantissa here is all zeros. But then you remember the mantissa, we do 1 plus m, so we add 1 on. So we get 1 times 2 to the power of 2, which is a value of 4. So this is our number here for our 4 and 16-bit floating point representation. And then we do something really strange. We take this number here and we just generate the binary equivalent. So all of these numbers here we generate, so they're going to be 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, 2, 5, 6, 5, 12. So it would be 1024 plus whatever this one is here. And whenever we add these up, in this instance here, we're going to get the number 17408. So this is just the normal integer number. So this here becomes our input to our fast inverse square root algorithm. So we take this, divide this by 2, take it away from 23040, and we get this number here. So this is the final output. So this number here should actually be related to 0.5. So we take this number here and then we convert it back into our binary representation. So we get our 16-bit binary representation of this number here, and we've got it written here. So this here is just the 16-bit binary representation of the integer number 14,336. So whenever you work out what this number here is, well, you're going to have 1, 2, 4 and 8. So 2, 4 and 8 gives us the exponent value of 14. So that's the biased exponent. And then we take away the value of 15. When you take away the value of 15, we get 14 minus 15 is minus 1. So that's 2 to the power of minus 1. Again, the mantissa is all 0. So we've got 1 plus mantissa is 1 plus 0. So that's this 1 here. So we've got 1 times 2 to the minus 1, which is 1 upon 2, which is 0.5. So you can see here that in this example, the fast inverse square root algorithm has taken the number 4 as the input, and it's given us the reciprocal of that square root. So it's given us the value of our 1 upon root of 4, which is 0.5, which is the number we are looking for. So this is a beautiful little bit of mathematics and a lovely bit of coding, and it's exactly the kind of thing that I love about computer science and the interplay between computer science and mathematics. Now, as we said, this is going to give us an approximation to the reciprocal of the square root. We can make the approximation even better by using something called the Newton-Raphson method. So it's the Newton-Raphson method applied to the inverse square root. Now I've got a little bit of the derivation here, but if you're interested, the final algorithm is written at the bottom. So we're going to take the output from our fast inverse square root algorithm, and then we're going to pass it through this Newton-Raphson method. So we're going to have the output, which is going to be yi. We're going to square it, multiply it by the value x, subtract it from 3, multiply it by y, and divide it by 2. Okay, and this is going to give us a better approximation to our square root. Now again, I've got the full derivation of this within the full 32-bit floating point unit division and square root course. So you can go into that course and you can have a look and you can see exactly how this is all derived. But we will see it implemented within our floating point unit. So the fast inverse square root algorithm is an approximating algorithm. Now we want to take this and then adjust it a little bit to make it a little bit more accurate for our purposes. So we're going to take the fast inverse square root algorithm and the Newton-Raphson, but we're going to change them just a little bit. So the first thing that we're going to do is, rather than have one magic number, we're going to have 10 magic numbers. So what the magic number in effect does, or what it looks like mathematically, we have an approximation to this function here, log to the base 2 1 plus m, and that approximation is approximately equal to m, which in effect is really just the magic number. But we're going to adjust the magic number by adding this little term alpha. So what does it actually do? Well, it means that between 0 and 1, we've got this function here in blue, which is log to the base 2 1 plus m, and we're going to generate 10 different magic numbers, which in effect are going to be the points here. So this point here, and this point, and this point, and this point. Okay, so we're going to linearize this function at 10 different points along the function, equally spaced. So that means rather than having one single line, say drawn from here up to here, which would be the normal approximation for the fast inverse square root algorithm, we're going to have 10 separate approximations, and each one of them will be a little bit better than the overall approximation. So that's the first thing that we're going to do. The second thing that we're going to do is that the fast inverse square root algorithm is not very good at numbers close to 0. So for the first, I can't remember how many, maybe 50 or 100 values close to 0, rather than using the fast inverse square root algorithm, we're just going to use a lookup table, and it will pull out the correct values for us, and that'll add a bit of accuracy. So those are the two extras that we're going to add into our circuit to make the fast inverse square root algorithm really applicable to our floating point unit. This is the original Quake 3 algorithm for a 32-bit floating point number. You can see here we have the magic number and we have the Newton-Raphson iterations. So they've got 2 iterations here. Now we're going to convert this to our 16-bit floating point number, and we're going to have 1 Newton-Raphson iteration. So in effect we're going to take this famous algorithm and we're going to generate the digital circuit within Logisim so that it is all hardwired. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.